Okay, let's talk about virtual memory and in particular how modern operating system use memory. Okay, let's have a quick introduction to the issue. Imagine that you want to write a program to find all the prime numbers smaller than n for a given n. So the well-known algorithm for this is this one. You probably might have heard it in high school or something. And so this algorithm can be easily implemented. It's very fast, and it just needs quite a bit of memory. So I looked it up online, and I copy pasted these pieces of code from internet for Python and Java. I'm not going to run them, but basically what I wanted to pay attention is to memory accesses. So this algorithm is memory intensive. It essentially assigns one integer per number between 1 or 2 and n, and then marks it as true or false whether it is prime or not. So when we look at these two programs, we'll see that these highlighted pieces are where we are accessing the memory. Of course, if you know your assembly language, you know that eventually these these lines in a high-level code, high-level language, will be translated to some code in the machine level that look like this example code that we have. So like these 2 lines of code. So essentially you're trying to move something from a register to a memory location. Okay, so this is eventually what it ends up boiling down to. If you look at it this way, you might be having some interesting questions, and that is where this memory address is actually located, and how is it possible for other programs not to write to your piece of memory? If you can write to a memory location, what prevents another malicious program from writing to your piece of code? Or if your code is buggy, what prevents your code from writing to a essential program that is running on your machine and corrupting their memory? To be able to answer these questions, we need to look at the concept of virtual memory. But before that, we have to remind ourselves that operating system is in charge of the memory. So in particular, the way the memory works is the following. So you have the physical memory represented up there. You have the operating system down here. And whenever a program wants memory, it will need to ask the operating system. So for example, your C program explicitly asks for memory from the operating system, says I need 50 megabytes of memory. The operating system checks whether there is enough memory. In this case, there exists, marks this piece of memory as belonging to the C program, and it returns an start address. And now the C program can use it, and the characteristics of a C program are the following: that we need explicit requests for memory, we need to know the memory sizes or array size in advance, all the addresses are known, and the coder is responsible for freeing, allocating memory, as well as using it properly and not go out of index, all that stuff. In a language such as Python, which is very high level, where you have these collections and the lists, and you can add things to a list without worrying about its maximum size, what is happening here is that Python is using some libraries, that these are the ones that allocate, manage memory, and do garbage collecting, all the stuff, but eventually they will need to ask the operating system, which will again do the same thing as it did with the C program. So in this sense, the library is different, but the essential mechanism is the same. So this answers the question of how your C program does not randomly write in somebody else's address, because it asks for the memory, and once it gets this piece of memory from the operating system, it knows that it belongs to itself. So therefore, it knows that it can only write in this piece of the memory. But it still doesn't answer the question of what if a code is malicious, or what if your code is buggy and you just randomly write to a different location in the memory? How is it that you do not corrupt somebody else's memory? To be able to understand that, we need to look at virtual memory. So I guess I'm going to skip this. All right. So now we want to get into virtual memory. But before doing that, let's understand 2 different ways of looking at the memory. So one way is to look at the hardware. So a memory, if you have a machine, you could have devices like this on a motherboard, that these are physical pieces of memory they can buy in a shop and just plug it into your machine, and suddenly you have your more RAM. In particular, what this means is that if you have some amount of data in your system, these data is stored as electric signals or electric voltages or whatever inside these devices. The physical location of your data is here. Okay, so that is what we call physical address. These devices have a particular way of talking to the CPU, so they have a location for every piece of their physical bytes and bits, and CPU can talk to them to ask for writing or reading of the information stored here. This is what we call a physical address. It is the address that the CPU needs to tell these devices to read and write data. Okay. There is also a software view of a address. So this is when you run an assemble instruction with a value or with an address inside your, say, move instruction. So inside this move instructions, we are doing indirect addressing. So we're referring a memory address whose address is given in the register RDI. The simple view of the memory that says these two concepts are the same. So if you're asking to read or write address 3, that means physical address 3. Address 10 in an assemble instruction means physical location 10, and so on. This is the simple view. The major idea or the big idea here is that this physical address does not need to be the access address. Virtual memory as an idea is the separation between these two modes of addressing. This is a fundamental idea that's going to change how devices work and how computers work. Okay. In this view, there needs to be a translation. There is a magic box that does the translation for you. It receives the value 3 and produces physical location 14. So now 3 could have nothing to do with 14. It's just a translation process, assigns value 14 to 3. The only thing this box needs to respect is that if you ask for the location of 3, it has to give the same answer, because you want to be able to do load and store to the same address correctly. But as long as this box is consistent, you have the separation between the address from the point of the software and physical location. This separation is what creates virtual memory. However, there is a particular implementation of virtual memory that is known as paging, and this is typically what people refer to when they mean virtual memory. So typically, virtual memory and paging is considered to be equivalent, but technically it is not. Virtual memory is a separation, whereas paging is a particular implementation of the separation. Okay, so let's try to understand how paging works. So in paging, you have we are dealing with two addresses. We have the memory or the virtual address as well as the physical address. To be able to understand these two concepts, let's look at an example. Let's assume that we have a memory that has 16 bytes. So this is my physical memory. It starts from physical address 0 up to physical address 15. And I also have 16 virtual addresses starting from virtual address 0 up to virtual address 15. Okay. Again, as I covered, the simple view is to say that this virtual address and the physical address are the same. But now we're going to look at a particular implementation that separates them. So one way of doing it is to do the following simple idea. Take your virtual address, which can be represented using 4 bits, because numbers from 0 to 15 can be represented with 4 bits. Cut it in half, say the 2 high bits and the 2 low bits. The 2 high bits, call them your page number. The 2 low bits, call them your offset. So these are just terminologies of the naming two different bits. Okay. Cutting the address in 2 parts, 2 high bits and 2 low bits, corresponds to the following operation when you look at the linear layout of these these bytes. So page 0 corresponds to the first 4 bytes of the memory. This is because when you write down the addresses of these bytes, you get the following. So 0 is essentially, of course, 0, 0, 0, 0, and 3 is 0, 0, 1, 1. Okay, can I write that better, please? 0, 0, 1, 1. Okay. So in other words, all of these numbers in this range from 0 to 3, they all look like this: 0, 0, some x, some y. Okay, so therefore their high 2 bits are 0. So therefore they belong to page number 0. Okay, and the same holds for page number 1. All the numbers in this range, if we write them in binary, are basically 0, 1, x, y. right? So all the numbers are unique, so they belong to page 1. Okay. So therefore, a visual representation of the cutting your address space in 2 corresponds to doing this operation on the linear layout of the memory. Okay. Okay. So now that we define this page number and offset, we can go back to the translation. So just to reiterate, so if you have a virtual address 0010, your page number is 0, and your offset is 10. Okay, and same for this one. All right, let's move on. So what you do here when you want to do the translation, you start with a table. So this table needs to have a row for every page number, and then a value corresponding to that page number that can be arbitrary. What you do here is that you look up your page number and then you replace it with the corresponding value in the row. So let's just look at an example here. So let's say we want to translate this virtual address 0010. So we start with 0010. We look up the page number, which is 00 in the row. So 00 needs to turn into 11. So let's try to do that. So we turn this into 11, 1, 1. The offset stays the same, so 10. So therefore, my virtual address 0010 translates to 1110. Okay. If I want to translate the other one, let me erase this. Okay. Let's translate the other address. So we have the address 0111. Again, these 2 bits are the offset and they need to be translated. So we translate them to the following. So we look at 01. So 01 goes to 00. And then the offset stays the same. So we get 00111 as a translation of this. As you might all notice in this table, the right-hand side column can be arbitrary. In particular, we have a repeated value 11 and 11 here. That's okay, or in other words, that's allowed. Whether or not that is correct or not, well, depends on the applications. And so there is no, fixed answer. Sometimes it could be right, sometimes it's wrong. And in particular, if your operating system doesn't have a bug, you trust that it always does the correct thing. Okay. A more complicated level of paging can be done by using 2-level addressing. So in this case, I'm not going to show you the layout of the memory because I have 6 bits, so that's too many I can't draw. But I have a 6 bit of addressing here, and now I have a 2-level paging. So you look up the first number, so in this case 11. So in this case 00. 00 needs to be translated into something that needs to be replaced by something, and it also needs to take us to some other location or some other table. Just to show an example of how this is done, for example, let's look at the following example. I have the number 110010, and my translation table, my starting translation table is the following. I look at 11, so that's your page number. You replace 11 with 10, with 10, and then we need to go to let's go in here. So this is replaced by 10. Then we need to go look at table 3. So we look at table 3. So we can find table 3 somewhere. Table 3 says replace 00 with 01. So we replace 00 with 01, and then the offset doesn't change. So therefore, the translation of the virtual address or this virtual address will be done to this virtual address. So essentially, it's the same idea, but instead of doing it in 1 level, it's done in 2 levels. This is the translation process that is used in practice. For example, if you look at Intel manuals, you will see a table like this. Intel, again, is terrible with naming things. So this IA32E is basically 64-bit mode of operation. Why they call it 32E, don't ask me, but Intel might be good at making chips, but they can't name things. So in this mode of operation, you have 48 bits of virtual address, and you can have page sizes of these different types. Typically, in most cases, you use 4K, and I'm going to show you this combination. So what I'm looking at is 64-bit mode of operation with 4 kilobyte page sizes. What this means is the following. First of all, in the 64-bit mode of operation, or the engineers and the designers, architects, they have decided that having 64-bit of addressing is too much because we're not going to have that much memory. Instead, so they decided to limit the maximum size of a virtual address to be 2 to the 48 or -1. This is already too much. That's terabytes or whatever of memory, so we're not going to get anywhere close to that, and it's like anytime soon. And if we get close to it, they will just add more bits to it, right? So no big deal. So basically, we have 48 bits to translate. Out of this 48, the lowest 12 bits is known as the offset. So this is what we don't translate. If you do 48 minus 12, you get 36. And 36 has been divided into 4 pieces of 9 bits. So you have 4 pieces, each one has 9 bits. They have different names, P, whatever, again, interval names. But the basic principle is the same. You have a register, a system register, CR3, which sounds familiar. This is what we've seen before. This register points to the root table, so the beginning of the table that is used for the translation of the highest 9 bits. So you look up the highest 9 bits in this table, in this mechanism that we've seen before. That tells you what to replace these 9 bits with, and then it takes you to the next table. That means that table allows you to replace the next 9 bits and then takes you to the next table and so on until you have translated the top 36 bits of your virtual address. And now you have the physical address of that virtual address. Okay. Typically, this is done by designated hardware. Again, to emphasize, this translation is done whenever an instruction tries to address memory. So assembly level, whenever you try to read and write from a memory location, it goes through this translation process. So there is no way for you, at least for now, is to directly access a physical location of the device. All your memory accesses go through this translation process. Okay, there are some details hidden in this diagram that I'm gonna ignore. If you want, you can look at the manuals. Okay. So what is the outcome of this translation process? And again, also this view is a modern view of virtual memory and operating systems. The older systems, or very older systems, obviously were different, but this is what we're gonna dealing with these days, and this is what I'm gonna stick with. What it creates is essentially can create one address space. So this is all the physical locations that a running process can access, because the access to the memory go through this translation process. So a process cannot access any location. It can only access designated locations. And this translation process, as I mentioned, basically goes like this. You have 12 bits and then 4 different page numbers that go through this translation process. And the interesting is that if you look at this translation process, what you realize is that if you have 2 virtual addresses that are identical except for the low 12 bits, they will get the exact same translation. Okay, so if you have 2 virtual addresses, something and 00, all the way to the same something and 111, since the translation process only changes this top these high 36 bits, it will not change the low bits. So therefore, all of these will be the same continuous chunk of physical location. This is known as one page, and that's why you get the name paging. All of these virtual addresses will belong to the same page because they will have same virtual location, essentially, or the same block of virtual location. And it also means that the smallest unit of memory where your operating system can allocate or free is essentially this size. So for 12 bits, if you compare 2 to 12, that's 4096 roughly, or 4 kilobytes. So 4 kilobytes in this model will be the smallest amount of memory that you can allocate or free. Okay. And so therefore, when people talk about page sizes, they essentially mean the 2 to the offset. So you might be wondering, why do we want to do virtual memory? We're going to look at capabilities later on, but I'm going to quickly summarize some of the issues or pros and cons of virtual memory. So the first thing that you might have noticed is that since we can allocate, or the smallest unit of memory that we can allocate is say like 4 kilobytes, this could cause internal fragmentation or unused spaces inside each space. Imagine that you have a program that needs 1 byte of memory. The operating system can only allocate 4 kilobytes of memory to this program. So therefore, all the 4 minus 1 byte will be wasted. If you have a lot of these programs, you will have most of your memory wasted in these blocks, basically. Obviously, if you reduce your page size, maybe you could go to, I don't know, 1 kilobyte page size or half a kilobyte page size. You could reduce this space. But the smaller page sizes means that now your translation process is more costly. You will need to either have larger page tables, or you could increase the depth of your translation, which will be actually the major bottleneck. So in particular, one of the major bottlenecks when it comes to virtual memory is that one memory lookup is suddenly translated to multiple memory lookups. If you remember to translate 9 bits at a time, we need to look into a table. That is already memory access, not for the programmer, but for the hardware. Hardware needs to fetch that location from the physical memory, which takes a long time. And in particular, virtual memory without caching is pretty much impractical. Caching is what saves us and makes virtual memory reliable. There will be some exercises, and we'll try to figure out what is the impact of caching on the performance of virtual memory. But virtual memory comes with a lot of different advantages. The first thing is that we could create the virtual address space that is much larger than the physical memory, and it's also independent of the physical memory. For every program, we could create this ginormous virtual address, and how this virtual address is mapped to the physical address, that could be decided by the operating system, but the programmer doesn't really care as long as it gets its own exclusive share of physical memory. It doesn't really care where the location of its variables are on the physical memory, right? So in that sense, it makes user or programming easier for the programmer. In the past, this is getting less relevant these days, but in the past, operating system would flush pieces of the memory that were not used to the disk to be able to get extra space, or to allocate more memory than is physically available. As we'll see later, having virtual memory allows the system to exert some kind of control on them. So you can have access control when it comes to reading, writing, or executing. You could share memory between different processes and all that stuff. And it will also have some impact in context switching, that we're going to talk about this later on. Okay. Let me just quickly through here. So just to cover sharing, what you could do with these virtual memory is the following. You could have different page tables for different processes. So that means that you could set up the following example. So you have one process that wants to access some memory location, and you could set up these virtual memory in such a way that processes 1 and 2, when they access the same address, they actually access different physical locations. So 1 and 2, even though they're trying to access the same virtual address, they actually go to different physical locations. So variables are completely different. Whereas process 2 and 3, even though they access different virtual locations, they are sharing that location. In other words, if one of them changes that location, the other one also gets changed. Usually that's not a good idea, but if processes 2 and 3, they want to collaborate, maybe they want to have a piece of memory that is shared between them so that they could exchange information. So in that sense, you could set it up. It also allows the operating system to do a lot of different optimizations. We're going to look at this through exercise classes later on, but basically you can do the following. Imagine that you have a program that runs twice, right? So you want to run the same program multiple times. Then the code of this program, since it doesn't change, it can only be loaded once into the physical memory and shared between these two processes. Same thing happens with library. You have a bunch of programs that are using the same library. Since the code of this library doesn't change between different executions, you could load this code once into the physical memory and then have these processes share this physical location. To be able to do all of these things, you need to have the code marked as read-only, which you would like to do it anyways for the terms of security. But once you do that, then there is nothing prevent you from doing this optimization, and operating system already take care of this this feature to reduce the amount of physical space or physical memory needed by the architectures. Finally, and also crucially, having virtual memory allows you to avoid external fragmentation. To understand this issue, consider the following example. Imagine that our memory is empty, represented by this empty box. And now let's say you're running a program that requests that amount of continuous memory, say, in one array. So you're trying to allocate an array that big. The operating system at the beginning says it's fine because the memory is completely free, so allocate this amount of memory to the program. Then the program requires even a bigger array of that size, and the operating system can oblige this and say, okay, this now belongs to you. The program next could say, I don't need the first array that I allocated, so I'm freeing that piece of memory. So now that piece of memory is freed. What you will notice here is that the free pieces of the memory are not in continuous blocks. What this means is that the next, if the programmer requires to allocate a slightly bigger array than the first one, for example, this array needed to be expanded because, we read more things from the disk or from network or whatever. So we need to enlarge this array. We can't do it. Even though there is enough space available in memory, there is no continuous space of that size available. Since if we have physical location equals addresses, we cannot remove or move the green spaces around either. So basically we are out of memory. We cannot allocate an array this big even though we have a space for it. With virtual memory, what you can do is the following. You could set up your translation tables such that this lower part of this array gets translated. So this part gets translated to this physical location, and this part gets translated to that physical location up there. From the point of view of user or the programmer, this is continuous. This block of data is completely continuous. So it can be worked as an array. So even though our physical locations are not continuous, from the point of view of programmer, they are. And this allows us to avoid external fragmentation, and we could use whatever amount of physical memory left as one block of continuous memory. So that covers the discussion of virtual memory here.